First, need to introduce Ron. So, uh, Ron Weiss did his PhD at Columbia. He graduated in 2009, then went for a year as a postdoc at NYU and joined Google, where he's been working on many things related to music and robust speech recognition. And he's going to talk today about training neural network acoustic models straight from waveforms.
That's right. I have a mic. Thank you. I don't think I can use this. Yeah, that work? That works. Sweet. Hello. Thanks for the introduction, Jonathan. So yeah, I'm going to talk about acoustic modeling directly from waveforms. Maybe we can finally throw away at least part of our 25-year-old MFCC code, hopefully. So this is joint work with a bunch of people in the acoustic modeling team here. Tara Sainath, Kevin Wilson, Andrew Senior, Arun Narayanan, Mikhail Bakiani, Oriol Vignels, and Yedid Hoshen. At least Kevin and Arun are here today, so if you have any questions, you can ask them too. All right. So I'm going to talk, this is a quick outline. I'm going to give a little bit of a review, DSP review, talk about filter banks, which hopefully most people here are pretty familiar with already. I'll talk about how that relates to this new deep neural network thing that we call a waveform CLDNN. I'll talk a little bit about what these things actually learn and then how to extend it to work on multi-channel waveforms. So let's see, the first half of this talk was presented at Interspeech a little while ago, I guess in September. So if you were there and you've seen that, you can fall asleep for the first part of the talk, nothing new. The second half is going to be presented in a month and a half or so at ASRU. So in the spirit of Back to the Future Day, if you've seen that talk already, just go have a coffee. Nothing to listen to here. All right. So acoustic modeling, what does that mean? Again, hopefully everyone here knows this to some degree at least. The idea is you get some long waveform, speech waveform, and you want to chop it up into small, maybe 10 millisecond long frames. And for each one of those, you want to classify, you have a big multi-class classifier, and you want to figure out what context-dependent phoneme state that corresponds to. Okay, so you're just taking this long signal and turning it into sequences of phonemes. And the way this is normally done is you compute some kind of feature representation, usually a log-mel spectrogram, like this guy over here. Can you see this? Yes, you can. All right, and so each one of those columns of that spectrogram, you want to pass into a classifier and usually a deep neural network and get posteriors over a big context-dependent phoneme state space. So this is kind of a little bit unsatisfying if you compare it to our colleagues in computer vision these days, because they tend to train big, huge deep neural networks directly on image pixels. They don't do any feature extraction at all, let the deep neural network do its magic, and they work pretty well, but we're sort of still have one foot in the olden days, if you will, doing manual feature extraction. So it would be nice, maybe, if we could catch up with them, in a sense, and train these things directly on the raw time domain samples and let the feature extraction all happen inside the neural networks. So quick review. How do we compute these log-mel features? We usually will compute the spectrogram like I showed over here, column by column. Right? You take your long waveform, you cut it into small overlapping chunks. For each one, you take the FFT, you take the magnitude, throw away the phase, do a linear transform to put it in MEL frequency space, take the log of every dimension to do some dynamic range compression, shift your window over, do it again, and you compute this column by column. You could also compute these things row by row if you wanted to. And what you do here instead is you take your whole waveform, you pass it into a parallel bank of bandpass filters of some sort. Again, do some kind of pointwise nonlinearity on the output of each one, usually like a full wave rectifier or something like that. Maybe do some smoothing, downsample it, take the log again, and now you've got a row of your spectrogram. So I mean, this computes basically the same thing. And this kind of thing shows up a bunch in the speech literature. If you remember things like cochleograms from way back in the 80s, I think, or gamma tone features, which have seen a little bit of use more recently, this is usually the way these things are computed. So if you kind of look at this a little bit and squint, you'll notice that each one of these boxes looks like something that you've seen before in a deep neural network. So if your filter is an FIR filter, that's just a convolution. We train convolutional neural networks all the time. Pointwise nonlinearity, well, a rectified linear unit is just a half-wave rectifier, so we already know how to do that. Downsampling you can do with some kind of pooling operation. And you don't normally see a log-like nonlinearity, but it's a differentiable function. You can backpropagate through it. So, there's some hope that we can learn how to do these things. And so the idea is, just like in the column-wise case, we're going to take a long waveform, break it up into small overlapping chunks. For each chunk, pass it into one of these neural network time domain filters, get a frame of features, pass that up to the upper levels of the network, hopefully be able to do a good job doing acoustic modeling. All right. So, I mean, there's nothing really new here. This is stuff that people should see in any at least moderately advanced DSP class. And so, it's an obvious idea, I think. People have tried it before, but unfortunately, no one has had really good success. So, a bunch of different things have been tried. This work out of Toronto from Navdeep Jaitley and Jeff Hinton tried to do unsupervised representation learning directly from waveforms. They built a deep convolutional autoencoder, trained that for a little while, and once that had been trained, put a deep neural network on top of it, tried to do phone recognition. It worked okay, but not as well as log-mel features passed into a similar neural network. Some other more recent work has just tried passing waveform samples directly into a fully connected deep neural net. It's not really doing filtering in quite the same way, but the story is similar. It works okay, but not as well as log-mel features. And a whole bunch of people, including us with an intern that Kevin and I hosted, I should say Kevin hosted a year and a half ago, tried to do this just with a convolutional front end, so a lot more like the sort of traditional time domain filter bank. The story is again the same, right? No one has yet shown any performance improvement or even matching performance to a log-mel based baseline neural network on a large vocabulary speech task. We're going to see if we can change that. All right, so what have people tried before that didn't work? So this is, again, the work. Actually, this was presented as a poster at SANE last year, so it might be a review for some people. So this is, we called it a deep waveform neural network, and it's exactly what I described before. We chose the parameters of this time domain filter bank neural network layers to match a log-mel. We had a bank of 40 filters, impulse responses that were 25 milliseconds long, matching the normal window size we use, hopped by 10 milliseconds, so the framing was the same. And then this is a deep neural network, so usually what you do here is you stack a bunch of these frames together and to give a little bit of context to the neural network, and then pass it into several stacked layers of fully connected units. So the actual feature representation looks something like this. It's got 40 rows and 26 columns of context. So if you're computing it using a neural network, we'll call it a brainogram instead of a spectrogram, but it looks pretty similar to what you do in a normal context. So one thing that we found, which other people had shown before, but I'll highlight anyway, is that including that log nonlinearity after the filter bank actually helps a bit. It gives you a performance improvement of 3 to 5%, so that's nice. But again, overall, the best system that we had was about 5% worse than the baseline, which is kind of unsatisfying. And so in parallel to that, our colleagues in the acoustic modeling team have been working on the latest and greatest deep neural network architecture for acoustic modeling, which is called a CLDNN. And CLDNN stands for convolution plus LSTM, so some kind of recurrent long short-term memory layer plus deep neural network. And the idea is you just stack these things together. You start off with some convolution across frequency, which is a little bit unusual maybe, of your feature representation. That gives you a little bit of invariance to things like vocal tract length maybe, or pitch. Pass that into a deep stack of these recurrent LSTM layers, which model the sort of long-term temporal context. That's what's doing the heavy lifting, really. And then you take the output of that, pass it into a couple of layers of normal, fully connected deep neural net. And that basically learns a nonlinear classifier on top of whatever the LSTM is learning. And so this works. I mean, the addition of the frequency convolution and the DNN gives about a 5-ish% improvement over a baseline that's only using a DNN, LSTM rather. So, stacking, combining all the tricks helps you a little bit. And the other thing that's kind of attractive is about LSTMs in general, really, is you don't need any context frames anymore. You can just pass one column of spectrogram into this thing, and it works pretty well. And basically what's happening is the memory inside the LSTM layers is remembering whatever context it needs from the previous inputs. So you don't need to mess with the features too much. All right, so we know a little bit about modeling waveforms. We know a little bit about how to do a pretty good job at, I guess we know a lot about how to do a pretty good job at acoustic modeling. So let's just match these things together. And thus was born the waveform CLDNN. This is exactly like the CLDNN that I described before, except now instead of passing log-mel filter bank features in, we're going to pass a waveform into this time convolutional layer, again set up to match the log-mel parameters. So it's learning 40 filters. They're 25 milliseconds long. So in order to get a little bit of shift invariance, we put in a 35 millisecond window for every step, convolve a 25 millisecond long filter across that. And in the 10 milliseconds that totally overlap between the filter and the input samples, we do some pooling, get one frame, computed entirely in the neural network. So this whole thing, it's pretty big. It's got about 19 million parameters and, very, very small number in the convolution. So we're adding a little bit of, a few more parameters to this neural network, a little bit more capacity, but we're giving it a much simpler representation of the input. And, let's see if this works. The whole thing is trained jointly in a supervised way. We're not doing anything too fancy. All right, so we did some experiments. Sort of large vocabulary task, an English voice search task. So talk to your phone, send Google queries, Google searches and things. We had a clean data set that's pretty big. It's got about 2,000 hours of training and about 20 hours for testing. And then also, just to make our lives a little bit harder, we wanted to try some multi-condition training. And so what we did is we took this clean data set and passed it through Room Simulator to simulate some reverb and mix it with a bunch of noise signals to make it noisier, and the hope that maybe, we wanted to see how robust this sort of thing could be. So the SNR of this data set on average is about 20 dB. The average RT60 is about 160 milliseconds, so it's a little bit reverberant and a little bit noisy. It's not terribly hard. And it's a little bit more far field, right? Normally in a voice search task, you're talking to your phone like this. Now the average distance between the microphone and the target is more like 3/4 of a meter, so it's a few feet away. So it's a little bit different. So, all right, we train our acoustic models. It's got about 13,000 context-dependent state outputs. It's a big, big multi-class classification problem. And we train it in the way we train lots of things at Google. Get a few hundred machines, do asynchronous stochastic gradient descent. You optimize the cross-entropy loss against some forced alignment. Wait a few days, get a trained model. All right. So how does this work? It works pretty well, actually. So if we look at the performance on clean data, we see that we're actually beating the comparable log-mel CLDNN a little bit. I mean, I claim that matches performance more or less. And if we train on the noisy data set, we get the exact same word error rate. So, we did something, and all of a sudden this works. We'll see in a minute why this works compared to what people have tried in the past. The other thing that was kind of cute is if you stack log-mel features on top of one of these convolutional layers, train the whole thing, and let it go, you can learn a complementary representation, basically, to the MEL filter bank and get a small improvement compared to just learning a filter bank on its own. So there's something interesting happening here. So what is the secret sauce? And the answer is memory. LSTM layers help you quite a bit. So we tried to train a comparably sized, fully connected deep neural net. So unlike our earlier deep waveform work, this is actually a big monstrosity of a neural network. It works a lot better than the small one we trained in that paper, but we still see a pretty big performance gap between the log-mel and the waveform. This is about a 4% difference. And so back to the CLDNN, what we can see is if we only have one LSTM layer, there's still a moderate performance gap. Everything gets a little bit better, right? So LSTMs are a good idea in general, but they seem to be, they're a good idea in general, but this is still not quite enough to get good performance out of this waveform model. So if we add more LSTM layers, all of a sudden they start matching. Even more, the performance of the whole thing gets a little bit better. So the idea is you get a little bit of shift in variance out of the convolution and pooling that we have in the front end, but you probably need something a little bit more sophisticated to do a good job modeling the long-term temporal context if you want these things to work. All right, LSTMs, good idea. Or, yes. So more recently, we tried the same sort of thing, but now we made a much noisier data set just to see how these things worked. So thus was born this MTR12 data set, which is exactly the same as MTR20, except the SNR is lower. The average is 12 dB. It's got much more reverb on average, and it's more far field, so the direct to reverberant ratio is going to be a bit lower. And here what we see is quite consistently the waveform model starts doing a good bit better, than the log-mel. So the other thing that we tried is we tried making these models bigger, right? Instead of passing in the normal 40-dimensional MEL filter bank, we doubled that in size and we get a small performance improvement. We went up to 128. We get a little bit more of a boost, but this thing gets way better if you give the waveform model more capacity. So this is really easy to tune, right? You just say, all right, I'm not learning 40 filters anymore. Give me 80 or 128, whatever. Initialize them randomly, it doesn't matter. This thing, let it learn for a week and it just works. I was amazed anyway. All right, so what do these things learn? So the hope is that it would learn a representation that's somewhat comparable to what we've been using in speech recognition for the past 30 years or whatever. And indeed, it kind of does. So over here, I'm plotting the normal sort of MEL triangular windows that we're all used to seeing, although it's on a log intensity scale, just so we can match things. And over here is the comparable magnitude responses for one of these waveform models with 40 filters. And so the way we built this is we took our impulse responses that this thing learns, we took the FFT magnitude to give us a magnitude response, and then we sorted them in ascending order of the bin that had the highest response. All right, so you can get something that looks like a filter bank that's ordered in order of ascending center frequency. And so what we see is that, for the most part, this is learning bandpass filters, and it's learning pretty narrow filters in the low frequencies, but as you get into higher frequencies, they get wider and wider. So, you see a similar sort of thing in MEL and in other auditory filter banks. So, it's kind of learning what you'd hope it would. One thing that was sort of interesting is it's learning a pretty different frequency scale from the MEL. If you look over here, there's only about 10 or 12 filters that have a response below 1 kilohertz. But in the waveform model, we get more like 23, 20, something like that. So it's putting a lot more resolution into the low frequencies, presumably because that's important, and correspondingly less resolution in the high frequencies. In fact, there's only like 4 or 5 filters over here with any response above 4 kilohertz compared to 10 in the MEL. So, tuning the filter bank parameters to your task might be a good idea, turns out. All right, so what happens when we add a bunch more filters? So again, this is the same view, similar view to the 40 filter bank I showed in the previous slide, and this is the version with 128 filters. So a couple of things stand out here. One is this is still, if you look at it from a distance, it looks like it's learning a bunch of bandpass filters, and it still has the same sort of a whole bunch of filters in low frequency and sort of logarithmic tail over here that's learning representation in high frequencies. That's kind of nice. But if you look a little bit more carefully, we'll see that, man, that's annoying. Go away. Okay. There's something like 80 filters below 1 kilohertz in the in the big model, which is kind of crazy, actually. If you took an FFT of a signal that, a window that's 25 milliseconds long, 400 samples at 16 kilohertz, you only get 25 filters below 1 kilohertz. This thing is learning 80. So what is it doing? I mean, it's got to be somewhat overcomplete, probably. And in fact, if you zoom in over here, that's what you find. You get a whole bunch of bandpass filters that basically look like a Fourier transform. But in addition to that, you get these more complicated shapes. You get filters like this one, which is learning a harmonic stack, or this one, maybe. You get other filters that are just the same center frequency as ones that we've seen before, but they're different bandwidths. So this thing is actually learning in the first layer to try and match things that look like speechy kinds of signals, because somehow that's a better use of its capacity than to put more resolution in high frequencies. So it's kind of cute. It's hard to say exactly why this is the right thing, but it seems to work. OK, so that's single channel. It works pretty well. Tuning your filters to match the task at hand might be a good idea. So what if we had a microphone array? And we were not in World War I. A common approach to doing this, if you've got multiple microphones, you want to build a noise robust speech recognition system, you'll probably split this into 2 stages. You'll do some kind of multi-channel speech enhancement, which usually amounts to doing some localization, trying to figure out where in space the target source is and where the noise is, then doing some linear spatial filtering in the form of beamforming to enhance the signal and maybe throw away some of the noise if you can. Pass that maybe into some nonlinear post-filtering. And at the output of this whole thing, you'll get a hopefully cleaned up single-channel waveform. Then you'll just pass that into a normal single-channel acoustic model, probably retrain it to match the artifacts introduced by the first one. But the acoustic modeling part is really no different from what you've seen before. So this is the same story as before. This is a little bit unsatisfying. Maybe it would make good sense to tune the enhancement to match the task that you actually care about. So maybe we should train these things jointly. And again, we're not original at all. This has been tried before. Mike Seltzer and et al. Tried this with GMM acoustic model about 10 years ago, 11 years ago, and found that it worked reasonably well. We're going to try the same thing, but we're going to use neural networks. OK, so another very brief review of filter and sum beamforming. So the idea here is you've got inputs from C different microphones, and we want to do some linear filtering of them to produce a cleaned up single channel waveform. OK, so this is the kind of setup you might have. You've got 4 microphones. You've got a target source that's located way over here. And if you measure the direct path between the source and each microphone, you'll see they have slightly different lengths, right? So the way you will usually do this is you'll try and figure out what the corresponding delays are between the source signal and each microphone, then just shift the signal that you recorded each microphone to compensate for that delay. So you get these, you get these aligned signals over here. And then you just take some weighted combination of them, or in this case, a filtered combination of them, to get a cleaned up single channel waveform. So this is, it's a multi-stage kind of process. You need to do some localization, figure out exactly what these delays are, and you need to figure out what the right filter weights are. So there's a bit going on there, and we're lazy. So we don't want to try and do any localization. Instead, what we're going to do is we'll rewrite this equation and absorb these shifts into the filter, and we'll get something that looks like this. And as a result, right, we're going to do some spatial filtering, but the direction in which we're looking is fixed. These filters are fixed. They can't. There's no adaptation here. It doesn't change from input to input. There's no localization at all. And so in order to make up for that, what we're going to do is we're going to learn a whole mess of these things, right? Instead of just having one filter across each of the channels for one particular instantiation of target sources over there, noise sources over there, we'll just learn a whole bunch of these things, and hopefully it'll capture the whole space that we care about. So if we look at this equation, it's not doing anything different from what we've seen before. It's just doing convolution in the time domain, except now instead of having one filter for one microphone. We've got C filters for C microphones. But the output of this thing is still a single channel waveform. We can still use the same pooling tricks and whatnot that we had from before. So let's build a multi-channel waveform CLDNN. And this looks exactly like the single channel waveform CLDNN, except now instead of having a single channel input here, we've got multiple channels. Here there's two. And for each, we pass that into a bank of filters, and each one of those filters now has C impulse responses, right? C is 2 in this case, 1 for each microphone. We take the convolution of this one with this one, and this one with the green one, sum the output. Now we have a single channel waveform, max pooling, log, etc. It looks just like the single channel case. So let's train this and see how it works. Again, data. So multi-channel processing probably doesn't help you too much if you don't have any noise to filter out. So we worked on this MTR20 data set, but instead of just simulating one microphone in a room, we simulated an 8-microphone linear array. So this array spans 14 centimeters, it's about 5 inches or so, and there's 2 centimeter spacing between each microphone. And we did this in a really, really multi-condition sort of way. So there are 100 different rooms. For each utterance, we pick a random room, we pick a random location to put the noise in, and a random location to put the speech in. And we do this for 3 million utterances and get a big data set. We do the same thing for our test set. And we're going to look at different subsets of microphones. So we'll look at the single channel version of this, which we've seen before. 2-channel, which just looks at the outermost microphones. 8-channel, which looks at all of them. And a 4-channel version, which is just sort of sampling every other microphone. So the aperture of this array is always the same for now. So how does this work? The answer is it works pretty well. Let's see, start at the beginning. We can also do this multi-channel enhancement trick on log-mel features if we want to. You just compute a log-mel spectrogram for each of your microphones, stack them on top of each other, pass it into a CLDNN. And that works okay. You can get a 2% absolute, 2.5% improvement by doing this. But as you add more microphones, it doesn't really help very much because, I mean, there's no fine time structure anymore. You've thrown away the phase when you compute these spectrograms, and your window is 25 milliseconds long. The actual inter-microphone time delays on the order of fractions of a millisecond, maybe a millisecond for an array like this. So you don't have that structure anymore. You can't use it. But the waveform model doesn't have this problem because it's doing everything in the time domain at the same sampling rate as your input. It can actually do spatial filtering if it wants. And so we see that if we have 128 filters, this waveform model works a good bit better. For 2 channels, it's pretty close to the log-mel, but as you add more channels, it gets better and better. You can go up to double the number of filters, and it gets better and better. In the 2-channel case, it's not a big difference, and that's because there's only so much spatial steering you can do with this 2-channel array. But if you give it more microphones, you can get bigger performance improvements. And what's happening there is just the number of nulls that you can steer with these things with an n-channel microphone array is n-1. So these things can learn more and more complex spatial responses if you give it more a denser array. That's all that's happening. Okay. So same story. What's the secret here? The answer is use LSTM layers. As in the 1-channel case, you start throwing away LSTM layers, your performance starts going down. It's a pretty big gap between a single LSTM layer and 3 layers. You start to bridge it by adding 2, and it starts to saturate it around 3. If you add another layer on top of that, you get a pretty incremental improvement. So LSTM layers, stack them. It's a good idea. Okay, so what does this thing learn? So it doesn't really make sense to talk about the magnitude response of these filters because you've got multiple microphone inputs. So instead, we're going to look at this thing called a beam pattern. And all that is the magnitude response as a function of direction of arrival to the array. So this is an example filter that this thing learns. And you can see there are two channels here. Blue is channel 0, green is channel 1. And they're learning basically the same sort of shape, right? It looks like this tapered window modulated with some sinusoid, except there's a phase difference between the two channels, right? So that's what's doing the actual spatial filtering. And so what we're going to do is we're going to pass two impulses into this thing. You know, if you pass it in with no delay, you're just mixing these things together. If one of the channels is delayed relative to the other, you're basically shifting, say, the green channel over a little bit move it to the left or something so that it reinforces with the blue channel, and you'll get an enhanced response if you move it a little bit to the right so they're exactly out of phase. They'll cancel each other out, and you'll get a decrease in the response. And so if we look over here, this is the beam pattern. Every row corresponds to a different relative microphone delay. And you can see this thing is learning a bandpass filter. It's got a peak at, if only I could see the frequency axis, a peak at around 1 kilohertz for most directions. But as we change the delay, at some point, these two channels start canceling each other out. That looks like it's at about 75 degrees using this scale, and we get a null, right? So this filter is learning how to respond to signals at around 1 kilohertz, as long as they don't come from about 75 degrees off axis. Spatial filtering, that's all. So now we can look at a whole bunch of these things. This is sort of a zoomed out view of this 128 filter bank. And look at what it's learning. It's basically, you know, it starts off with low frequencies, learning pretty narrow band spectral decomposition, but we'll see that it's got these nulls all pointed in different directions sometimes. This one is basically, doesn't have much spatial response. It's the same impulse response in both channels, more or less. And in high frequencies, you see the same sort of thing. They get the bandwidths of these filters get wider and wider, and you stop seeing so much spatial response because the array is not sampled finely enough in space, actually, you get spatial aliasing and things. And even in general, there's not much use to spatial filtering speech above a few kilohertz. OK, so the frequency scale here, I'm not showing it to you exactly, but it ends up being pretty similar to the one that you learned in the single channel case. And again, about 80% of the filters actually have a significant difference in the spatial response in different directions. So this is learning how to do spatial filtering. And if you zoom in a little bit more, you'll see that it actually ends up learning basically the same exact filter in several cases, but steered in different directions. So this one, right, we've got two filters that have basically the same shape. Man, that scale is pretty bad. They're responding somewhere around 700 hertz or something like that, but they're steered, you know, in different directions. One is a null over here, one is a null over there. So you could sort of imagine that what this thing is learning is several different spectrogram-like representations with nulls pointed in different directions. So it's sort of sampling the space of frequency and direction. Not uniformly, but think of it that way. And then something upstream, right? The top levels of the network learn how to combine these things in a way to figure out, well, maybe the spectrogram over here is the target source. That's what we care about. And the spectrogram over here is mostly noise. We can throw that away. And that's what enables it to do better speech recognition in noise. OK. All right, so we're doing beamforming, sort of, in this network. We might as well compare it to an actual beamformer. So we built this sort of best case, really simple beamformer that you can imagine, which is just a delay and sum beamformer where all you do is you take we simulated this data set, right? So we know where the target source is. So what we're going to do is we're going to align all the channels, mix them down together, get a single channel waveform, which should enhance the signal coming from the target direction and do a little bit of filtering out of the noise coming from other directions. And this is totally cheating, right? We know the time difference, the best we could do. We don't have to do any localization. And we see that, you know, this performs OK. It gets better and better as we add more channels. But consistently, the waveform model does better. And so this is maybe a little bit of evidence that we don't have to do explicit localization. The network is learning how to do this for us. And we're getting something that's somewhat invariant to the actual direction of arrival, which is pretty nice. So that's sort of maybe a best case scenario. But what if we were in a world where you've got real users or something like that, and your microphone array at test time doesn't match what you had during training, right? You gave your microphone array to a young child or something. They broke it in half and made the two microphones closer together or something. So you'd expect that something that does fixed spatial filtering isn't going to work very well. And indeed, that's what we have. So again, this Oracle delay in sum is kind of the best case since we're cheating. And even in the mismatch case, we know what the correct shifts should be for each channel. We should get something that's reasonably invariant to spacing, and indeed we do. It gets a little bit worse as your spacing gets narrower and narrower, but and that's just because of the spatial resolution of the array is changing. But for the most part, it's pretty invariant. But our waveform model that was trained, it only saw 14 centimeter spacing. You test it on 14 centimeter spacing, works really well. But as you start changing the spacing during test time, it gets worse and worse. It's not too much of a degradation if you only change it a little bit. But if you go down to, you've trained on a really wide array and you test it on a really narrow array, your performance goes to hell. This is like 50% worse than the match case is over here. And so we have this sort of weird 0 centimeter microphone array where you just take the channel, the signal from microphone 1 and you repeat it twice. So it's sort of, you're averaging, you're doing some weird spatial averaging of a single channel signal. That doesn't work very well. All right, so multi-condition training, it seems like a pretty good idea in neural networks and in speech recognition or data augmentation. It's sort of the same thing. Let's try it here. So what we did is we created this data set, which we call multi-geometry training set. And all that was is we took the 8-channel training data that we have, and for every utterance, we just picked 2 channels at random and used that for training. So sometimes you're training on the same microphone. That sort of matches the 0 centimeter case. Sometimes you're training on the outermost. Sometimes you're training on the 2 in the middle. Sometimes you're training on the 2 in the middle, but swapped. But lo and behold, this works. And what you end up with is a network that becomes invariant to the spacing of your microphone array. And you get basically no performance degradation at all as you change the spacing. And it works really well in the single channel case too. So win-win. All right, so what the hell is this thing learning when we train it on this multi-geometry data set? I mean, it can't really do spatial filtering because it's not seeing a consistent view of space, if you will, during training. And in fact, it doesn't. So these are the filters that I showed you before in the fixed geometry model, and these are the kinds of filters that we see in this multi-geometry model. And so we're still learning a bunch of bandpass filters. There's now much more variation in bandwidth than we saw before, but there's no more nulls. There's really no more spatial filtering in the sort of traditional sense, although there's a little bit of spatial information that makes it through this, in that you can see filters like this one, or even this one. They have a strong response in one channel, but almost no response in the other. So like this thing is learning how to average your 2 microphones together, and sometimes it's saying, well, here's the spectrogram you get if you only look at this microphone. Here's the spectrogram you get if you only look at this microphone. And it works. So somehow the rest of the network must be learning how to model the directionality based on this representation. I can't really explain exactly how, but it's something we want to look at. Okay, so one more quick round of experiments. This is a little bit unsatisfying in that this is all simulated data. The real world rooms aren't totally linear time invariant. So, we don't have an easy way to go get a whole bunch of microphone arrays, put them in a whole bunch of different rooms, ask people to talk to them, transcribe them all. So we settled for sort of a middle of the road, re-recorded situation where we took the room simulator out of the equation and basically put a microphone array in a room somewhere, mismatched to all the microphone arrays that we've seen before, got some speakers set up, played our test set through those speakers, so had and recorded them on the array. So the room is no longer simulated, it's real. We did the same thing with a bunch of noise signals, and then we artificially mixed them together, so it's still a little bit artificial, and followed the same kind of distribution as we had in the MTR12 set. And this is the performance that we get. So this array is twice as wide as the one that we've seen before, so it's still mismatched and slightly more realistic. But performance of all these models gets a little bit worse. So actually, the spatial filtering doesn't help you quite as much as it did before, because this is unlike anything that the network had seen before during training. It still works well in this case, but it doesn't work very well, or as well, I guess, on the re-recorded case. But this multi-geometry training has done the trick. So this is the best performing model that we have. So sort of the takeaway here is data augmentation, multi-condition training, mess with your data a bunch, train a big neural network, wait a while, maybe you'll get something that's pretty robust. OK, so that's about all I got. Just to conclude, the idea here is, maybe we can start thinking about going away from feature engineering and instead just work on deep neural network architecture engineering. The filter bank that we're normally used to using for feature extraction is something that whose parameters you can learn through backpropagation with big data sets. Works pretty well with supervised training. You can optimize it for what you are trying to do, so for speech recognition. I talked about this waveform CLDNN model, which does the trick. It works as well as a log-mel baseline on clean data and starts doing better and better as you add more noise. And you can train this thing to do spatial filtering as well, or I guess you can train this thing to process multi-channel inputs somehow and get even more noise robustness. The secret sauce is recurrent neural networks. LSTMs are a good idea. And multi-condition training also is a good idea. Train on clean data, train on noisy data, mess with your microphone array, pass it all through a big neural network, wait a while. It seems to work pretty well. So I don't know. You can sort of conclude that maybe we can throw away HDK finally and let our neural networks do the work for us. OK, that's all I got. There's a whole boatload of references if you want to read them. I'm happy to take any questions. Oh. Thank you.
Francis?
Probably want to pass a microphone around or something. Or not, yeah.
Thank you. Could you go back to what do these things learn, and then back about
this one? There are a lot of them.
back in the
single channel.
Single channel. Were you there?
Yep.
Exactly.
Yep.
Okay. So what about the smudges? Right.
Yeah. I mean, these things are not perfectly bandpass for sure.
Well, sure. So, but suppose you got rid of them. Suppose you dropped out those filters that seem to have very wideband response.
I see.
Would that break the system, or are they adding something pretty valuable?
If you have a pre-trained system and you threw away several of your filters, it probably wouldn't work as well.
Well, suppose you train the rest of the system on those.
Yeah, exactly.
Yeah.
It's kind of hard to say from this picture how important they are. I don't know. I don't want to make claims that they're actually not adding much just because they look kind of noisy. It's easy to imagine doing some kind of filter culling as a function of time, where like if you see something that's converging to a filter that doesn't look like what you'd expect, throw it away, start again. But we haven't tried anything like that.
I mean, I also notice looks like there's often a bunch of noise in the very highest band.
Yep.
And that's also, to me, somewhat interesting.
Exactly. I'm not sure entirely what to make of that. These are 16 kilohertz signals. And so maybe what we're seeing is maybe the anti-aliasing filter that we have is throwing away a bunch of the information between whatever that is, 7.5 kilohertz and 8. And so there's no signal there anyway, so it's able to learn noise. That's a total guess. I don't know.
Do you train these with a bunch of regularization? Because I could imagine if you really tried to get zeros.
Yeah, there's no regularization at all on this layer. We're not trying to make it sparse. We're not trying to keep it bandpass. This is nothing fancy.
Another question?
There's also someone over there.
All right, so maybe this doesn't matter for you because you're Google and you have an enormous amount of data, but it seems kind of unfortunate to be training the frequency responses and spatial responses independently. It seems like you would want a similar sort of structure to that in various directions. And have you tried building that in somehow, or?
That's a fair question. Yes, but we're not ready to talk about it, so stay tuned. Yeah, I mean, this whole thing, I would say, is just the beginning, right? We tried the dumbest things we could. Try and match a log-mail filter bank. Throw a lot of parameters at it in the multi-channel case. Let it learn something. There's still plenty of architecture engineering to try. So, yeah.
Sorry, Brian?
First, I want to say this was really interesting, so thank you.
Thanks.
I was just wondering, in terms of the horse race here, for example, and your mention of 19 million, was that right? 19 million parameters?
I believe so.
For those of us who don't have access to clusters, I was just wondering, could you imagine that you can learn something from this and say, well, okay, we knew, for example, that MEL frequencies were an approximation in the first place, and it would seem like you could have a lot fewer parameters to train if you, in a slightly different horse race, said, I'm going to, pick allow myself to vary my center frequencies, learn the appropriate center frequencies and cues.
Yep.
So that you might have I don't know, only 12 million parameters to learn?
Certainly you can imagine enforcing some kind of structure on these filter banks. I mean, you can think of that as a form of regularization even. But that's not really where all these parameters are going, right? There's only, it's like 0.1% of the network are in the filter bank. The rest of it is all in these LSTM layers and whatnot. So if you...
I guess my question was this: for someone who doesn't have access to your resources, would it be reasonable to what could we remove so that we could try and do what you're doing, but do it with 1 million parameters?
Yeah, wait a long time. It's probably not going to work as well with 1 million parameters. Also, I didn't talk about this in the talk. Go look at the InterSeach paper. It doesn't work quite as well if you don't train it on tons and tons of data. So I think it's kind of disappointing, right? Deep learning works, but only if you let it go for a long time. But I've never trained one of these things without a cluster, so I'm not sure, honestly.
I think we're running late, so maybe just one last question.
It's just to segue from that comment that most of your parameters are in the LSTM layers, and I can sort of, in a fuzzy, intuitive way, understand why that is important. But have you tried to pin down, like, if you don't have LSTM layers, do the filters look different? What is the exact quantitative difference?
So if we don't have LSTM layers, they, if you squint at them from a distance, they don't look very different, actually. So this first paper, this guy, that was at ICAST this year, no LSTM layers. It's actually a pretty small neural network. Still learns the same sort of thing. It's a different frequency scale from MEL. They're still mostly bandpass. So I don't think there's a lot of black magic in the filter learning. I think a lot of it is actually in the LSTM. And probably, we haven't actually tried this very carefully, probably what we're doing wrong here is we're trying to match the log-mail filter bank, right? Maybe the fine time structure matters more. Maybe we should use narrower filters. Maybe we shouldn't pool as much. And then maybe you don't need an LSTM. We just haven't tried it.
Just a quick yes/no question. For your multi-channel experiments, was your test data also simulated or recorded?
Except for the last slide I showed, the test data was always simulated. And this is quasi-simulated.
All right, let's thank Ron again. You can ask more questions during the coffee break, tonight during the closing remarks.